I will talk about methods extracting horizons and sequence boundaries from 3D seismic images. Before talking about my work, I'd like to show you an image of the current Earth surface, which is obtained by using the INSA technique. The INSA technique is amazing because it allows us to view the current Earth surface on a big scale. However, our seismic method is even more amazing because it can give us a view of buried ancient surfaces. In a migrated 3D seismic image like this one shown here, if we extract surfaces along seismic amplitude peaks or troughs, we are able to get seismic horizons. And we can think of these seismic horizons as buried ancient Earth surfaces. This buried ancient surface shown here is a seismic horizon we extracted from a 3D seismic image. It gives us a view of what happened many years ago. For example, it allows us to imagine that water and sediments came down as denoted by the red arrows here, and then funneled the channel to its end to form a kind of delta fan here. Of course, to get such a good seismic horizon with significant geological information, we need a good horizon extraction method. So in this presentation, I will have 3 parts. Firstly, I will discuss how to extract a seismic horizon by using one control point in simple cases. Secondly, I will discuss how to extract more accurate seismic horizons if we have more control points in complicated cases. And finally, I will discuss an active surface method to further refine these extracted surfaces to reveal more geological details. First of all, let's talk about how to extract horizons in simple cases like the 2 seismic sections shown here. These cross-line and inline seismic sections are extracted from a 3D seismic image which was provided by the DGB Earth Sciences. This is a simple case because all the seismic reflectors here are strong, clean, and continuous. To extract a seismic horizon, we first define a control point to indicate the seismic horizon we want to extract. Then we initialize a horizontal surface which also passes through the control point. So given this surface f, which is a function of x and y, we can compute the surface normal vectors by using its gradient components, fx and fy. And the alpha here is a scale factor to normalize the vectors. Of course, for such a horizontal surface, its normal vectors are vertically pointing downward. And at the same time, we can also compute the seismic normal vectors by using the structural tensors. As Dave talked yesterday, for each point in an image, we can construct a structural tensor matrix. And then we can compute the eigenvectors and eigenvalues of the structural tensor matrix. The seismic normal vector here is the eigenvector corresponding to the biggest eigenvalue. So as denoted by the blue arrows here, the seismic normal vectors are unit vectors which are normal to the seismic reflectors. If the extracted surface aligns with a seismic horizon, the surface normal vectors should be equal to the seismic normal vectors. However, for our initial horizontal surface, which does not align with any seismic horizon, therefore, the surface normal vectors here are not equal to the seismic normal vectors. So to update the surface to align with a seismic horizon, we want the surface node vectors to be equal to the seismic node vectors. Therefore, we need to solve this inverse gradient problem to update our initial surface to the seismic horizon we want to extract. Actually, formulating this problem in this way is not new. Nomask and Derek Parks did this to flatten an entire seismic image. But we do it here to extract a single seismic horizon from the seismic image at each time. And in this problem, the surface F is unknown, but we know both P and Q, which are actually reflector slopes, which are components of the reflector slopes. This means we have more knowns than unknowns. Therefore, we are looking for the least square solution of this inverse gradient problem by minimizing this function here. And to make the solution more stable for noisy image or chaotic reflectors, we add a surface curvature term to this function to be minimized. And minimizing this function here is equivalent to solve its corresponding Euler equation here. And we solve this Euler equation by using Fourier transforms. Now let's go back to the example. We first put a control point to initialize a horizontal surface. And this initial surface is updated by 1 iteration, 2 iterations, 3 iterations, 4 iterations, and finally, after 5 iterations, the initial horizontal surface is updated to the seismic horizon we want to extract. From a 3D view of the updated surface, the initial horizontal surface does not align with any seismic horizon. Therefore, the amplitude values on this surface change randomly. And during the updating process, this surface is gradually updated to the seismic horizon, and the amplitude values on the surface become more and more uniform. And finally, after 5 iterations, we can see that all the amplitude values on the surface are uniform almost everywhere except in this small part, which is highlighted by the black circle. So the extracted surface is not good enough here because we have more complicated geology here, and it's usually difficult to estimate accurate seismic node vectors in these complicated areas. So next, I will discuss how to extract more accurate horizons in these more complicated areas. Here we have a common Strata model. The horizons denoted by the blue curves are easy to extract because they continuously appear in the entire image. But the horizons denoted by the green curves are difficult to extract because they stop at some boundaries in the image, and usually we don't know where these boundaries are. So to extract these difficult horizons, we first need to extract the boundaries where these horizons stop at. And actually, these boundaries are called sequence boundaries by geologists, and they are important for geologists to define a depositional sequence. So for the sequence boundary extraction, its conformal parts highlighted in blue are easy to extract because we can estimate accurate seismic node vectors in this area. But its unconformable parts highlighted by the ellipses are difficult to extract because we are not able to estimate accurate seismic load vectors in this area because we have multiple orientation structures here. Here I will show you a real example to further explain the difficulties of extracting sequence boundaries. Using the horizon extraction method I just discussed before, I extract a surface by using one control point. And this extracted surface does align with the correct sequence boundary in its conformal parts, but it does not align with the correct sequence boundary in its unconformal parts. Therefore, this extracted surface needed to be further corrected in these unconformal parts. And here we provide a method to improve the extracted surface in these unconformable parts by using scattered control points. Now let's go back to the extracted surface by using one control point. We have learned that this surface is not good enough in the unconformable areas. But if we have more control points on the correct sequence boundary according to the geologists, we can compute the differences between the control points and the extracted surface. And we call these differences corrections. By using these corrections at the control points, we can interpolate a correction field CXY by using the thin plate spline interpolation method. In this interpolation function, its coefficients A1, A2, A3, and WS can be computed by using the corrections and the positions that we have known at the control points. Therefore, for each iteration of our surface extraction with control points, we have two steps. First, we update the surface by using the seismic load vectors after solving this Euler equation. And then we correct the updated surface fx by using the interpolated correction cxy to get a corrected surface fcxy. And this corrected surface is used for the next iteration. Here, I will show you an example. Actually, this is the same example of the sequence boundary extraction I just showed you before. And this, the blue curves here represent the surface we extracted by using one control point. And we have learned that this extracted surface is not good enough in the unconformable areas. By using treating three control points, we get a much better surface which aligns with the correct sequence boundary in both its conformable and unconformable areas. Again, from a 3D view, this is a surface extracted by using one control point, and we bring this surface to the correct position by using treating 6 control points. So now we have discussed how to extract a seismic horizon by using one control point in simple cases. And we also discussed how to extract more accurate seismic horizons or sequence boundaries in complicated cases. However, our story is not over here because these extracted surfaces can be further refined to reveal more geologic details. So now let's go to our final part, and I will take a seismic horizon active surface method to refine the extracted surfaces to reveal more geologic detail. So generally, the horizons were extracted by using the reflector orientation informations can follow the reflect structures, but they do not necessarily align with the amplitude peaks and troughs, or troughs, as we expect. So therefore, we propose an active surface method to further move the extracted surface to the amplitude peaks and troughs. This will reveal more geologic detail. Our active surface method is similar to the active slate method in the image segmentation. An active slate is a closed curve which is attracted by an external energy to automatically to move to the image boundary. And during its movement, the original shape of the curve is preserved by using an internal energy function. In our active surface method, we also define an internal energy, but by using the surface curvature term, as I showed before. This term can preserve the original shape of the surface and can make the surface smooth. And we also define an external energy by using the seismic amplitudes. This term will attract the surface to the seismic amplitude peaks or troughs. And for this external energy, if we want to align the surface with the amplitude peaks, we need to use a negative sign here. But if we want to align the surface with the amplitude troughs, we just use a positive sign here. So assume we want to align the surface with amplitude troughs, we get a total energy function by using its internal and external energies. And again, minimizing this energy function is equivalent to solve its corresponding Euler equation here. And we solve this Euler equation by using the Fourier transforms. Here is an example. The blue curves here represent a surface we extracted by using one control point. And the green curves here represent the surface we extracted by using 25 control points. Now the red curves here represent the surface after the refinement by using the active surface method. To look closer in these subsections, we can see that both the extracted surfaces without the refinement do align with the reflex structures, but they do not align with the amplitude troughs as we expect. And the red curve here represents the surface we extract with refinement exactly align with the amplitude troughs. And therefore, it reveals more geologic detail. For example, the structure of a subtle channel here can only be resolved by the red curve shown here. Again, from a 3D view, this is the surface extracted by using one control point, and this is the one with 25 control points. We can see that we have some improvements by using more control points because the amplitude values on this surface is more uniform than the one use only one control point. So now let's focus to say, but actually I want to say that both the two surfaces are kind of smooth. Now let's focus to see the surface after the refinement by using the active surface method. From this, we can show much more geologic detail which cannot be clearly observed in the previous two surfaces. So let me summarize everything I just talked about by using the same sequence, but the color here denotes the travel time. And in my presentation, I first discussed how to extract a seismic horizon by using one control point in simple cases. And then secondly, I discussed how to extract more accurate horizons if we have more control points for complicated cases. And finally, we discussed active surface method to refine the surface to reveal more geological detail. Thank you for your attention.